Hello everyone. I'm going to be talking today about C-exprs and Lexburs, or C-exprs and Lexburs. Here's a little example S-expression program that I pulled from one of the Racket guides. And when I look at this, part of me sees something really beautiful, which is that S-expressions have a very regular structure, and that regular structure makes them sort of, quote, trivial to parse, meaning that since it's all the same thing everywhere, it's very easy to parse and manipulate. There's this very simple tree that describes what's going on. And in Racket, we use lots of signs other than parentheses to add some structure to our programs. So for example, you can look at where it says current custodian, and there's a left bracket and a right bracket. So many people, when they start using Racket from the Lisp world, they're blown away by the fact that we use like two other symbols, and it's very controversial, but nevertheless we do. And then you can also see that we make heavy use of dash to name things. Now, part of me, the other thing is that we use a lot of indentation. So this program, like, if I were to not have indentation, it would be like practically unreadable. It would be very difficult to understand. Now, when we look at other languages, like C, for instance, so here's a version of this program in something that's kind of like C. So, maybe it's sort of like C and kind of like Go, I don't know, just kind of like C-ish. So one of the things that we notice about this is that there's more implicit structure here. So what I mean by that is that, like, notice that like fun, accept, and handle, and handler, and listen, like these things, they're like part of one unit in our mind, but they're not part of one sub thing inside of the syntax. So that means that behind the scenes, there has to be something that knows that fun has like these two things like inside of it, even though they're actually siblings. Now, that's something that doesn't really show up when you use S-expressions, because there would be a parenthesis right here and a parenthesis down here, and those things would tell us where the program was. Similarly, we see that there's other sorts of instances where siblings are associated, like here, and then there's also deeper structure when we have assignments like this. Now, something that's even more severe than this is a language that's like, that's like Haskell or Python that uses indentation as well. This program is like almost identical to the last program, except that I've added these colons right here and removed the braces. But now the idea is that the indentation here is forced. So something that I thought about a lot when we first started getting into the Rhombus project was how to produce something that is like S-expressions but has this structure right here. Now, there's obviously a gigantic amount of prior work on this where people try to define like indentation-sensitive S-expressions or things like that, where basically the main idea of these, if I were to summarize them, is that the real language is S-expressions, and let's just make it convenient to write those S-expressions. And I wanted to think about this a little bit differently. So let's zero in on S-expressions for a little bit. So S-expressions, they kind of have this syntax where the body of your program is a list of forms, and then forms are either atoms, or there's a left parenthesis, and then a list of forms, and then a right parenthesis. And then there's also this one other syntax, which is that you can have a dot right here, and then a form after that. So this is like an extremely broad thing. And now, of course, in Racket, we do things a little bit differently, where we have a very complicated atom syntax, and we also have like reader macros and the add expression, but this is roughly what the surface syntax is. And of course, let me say one more thing, which is that we also allow different things for the left and right parentheses, namely brackets and braces, but they're purely on the surface. They don't actually, they're not relevant to the parse. And the way that we parse it is to something that's basically like this, where we have atom, and then we have syntax, cons, syntax, and syntax. And, really behind the scenes, syntax cons has a little bit more information, so it has stuff like where the source location information was. It does record what's called the parenthesis shape, which is whether it was a left parenthesis, or, whether it was a parenthesis, a bracket, or a brace. And there's other stuff too, but this is basically what the surface syntax is. Now, my first experiment with this I called C-exprs, and, or C-exprs, which has the same pronunciation, but just a different way to write them down. And the idea here was to define a richer or more detailed parsing format. And so here's the parsing format that I came up with. And it's based on what C programs look like. So there are atoms, so there's things like numbers, symbols, etc. And then there are sequences of statements. And sequences of statements are like groups that occur inside of function bodies or on the top level. And then there are statements themselves, and statements themselves are things that are siblings of one another. So that would be like the fun definition, or like a return statement or something like that. And then inside of statements, there are also operations that are written in infix, and then there are applications where we record what the shape is, and we have the the function and then the argument. And then finally, because I wanted to deeply ingrain alternate syntaxes in text, I had the at form, which says that I'm calling this particular function, or well, here's like something that's at the front of the text, and then here's some text. And text can have a escape, which is the at form, or it can have a string, or it can have a sequence of texts. And so this right here was the format that I was going to target. And let's look at what the surface syntax was. It's a lot more detailed than S-expressions. So here's what the surface syntax I came up with was. Let me just move that a little bit. Okay. So the body of your program is a list of statements, a list of statements. That's what a body is. And then a statement is a list of expressions that's ended by a semicolon. And then we've got atoms. We have a special category of operators, which you can refer to alone, or they can be in prefix as a unary thing, binary, or you can use specific symbols, or you can have an application, and an application will have a shape of an opener and a shape of a closer. And then you can have braces for a body, and then grouping. And then braces for a body and grouping are invisible. Notice that they don't leave any residue in the syntax, so that means that you can't tell as a user whether you receive something with braces or with parentheses. So this is sort of like one of the goals that I had, that like parentheses would always be allowed. You could put them anywhere you wanted in your program. Then finally, there's an at form for text, and text just has escaping. You can embed more text, and then you can have any character. And so this right here is kind of the idea. Now, there's a lot more details that need to be specified, like what exactly are atoms, what are operators, what are the forms. But the idea is that like an example operator would be something like comma. And so since comma is an operator, that means that this function call form right here, you can have traditional function call notation because comma is just an operator. Similarly, you can have dot be an operator, and since dot's an operator, that means you can have, x dot y. And then since there are different kinds of shapes for openers, this means that you can have array notation, like array bracket x, be an example of a kind of application where we record what the kind of application it is. So let's look at a few example programs that are written in this form. So let me find a good place for my camera. Let's move it up here for now. Okay, so here's a little example. So you can have var x equals 3. And so this is a statement where there's var and then the operator equal x3. You can have function f, y, z, and then you have y plus x plus z. So you have a statement, which is fun. Then there's a paren shape where you have f and then the comma operator with y and z, and then some statements and one statement inside of that, which is an operator with x, y, z. So the idea here is that the parsing is going to collect multiple occurrences of the same operator and combine them all together. And so we can also have things like let. Here's a little bit of a longer example. So this is for a function called timed thunk, where we get the before, we get the after, and notice that we use parentheses, but they don't show up in the program, and then we just end with answer sitting by itself. And then finally, I wanted to explore what a macro would look like, and so here's an example of a macro. So the example of a macro here is that we say mac timed, and then we're going to implicitly do a parse of what's outside. And one of the reasons that we want to have the braces form is so that we can have timed behave differently when it is in a statement position versus when it's in a call position. And so here we can call, timed thunk and give it the thunk, or we can call timed and give it the E. And so the idea here is that the case can actually inspect. Notice that in the parse, it has syntax statements on the left-hand side of an arrow, and over here it has syntax app on the left-hand side of an arrow. And so the idea is that each one of these is going to be an allowable thing that we can do. So I experimented with this, and we talked about it a bit. And I think that there's some pleasant things about it, but I wanted to push harder with the experiment. And rather than just having something that was, S expressions but C, I wanted to, go a little bit deeper. Here are some more examples. Functions, we could have like colon be its own operator, which allow us to get name arguments. And this is kind of like a proof case where we can say, dictionary key.center.x, and this parses into something. But as I said, this wasn't terse enough for me. And in particular, one of the things I felt is that it didn't rely enough on the indentation, which is something that I actually use when I program a lot. And so I wanted to try to incorporate that. And I also wanted to nail down an actual implementation, because all of these parses are just made up. It's just sort of a design document. So, and sorry, I keep sort of transitioning to the next thing, but I forgot that there's one more example. I just want to show you what using the text form would look like. And so the idea is that the text form is going to be really useful for embedding other programming languages as well as actual text. So here's an example of including the data log. All right, now finally we can talk to the other thing. I was kind of rushing through C-exprs because I think they're cool and I do like C syntax a lot, but I spent a lot more time on Lexburs, and let me describe them a little bit. So the idea here is that we want to have something that is indentation sensitive, but indentation sensitive and completely structured, like S expressions are. And I had some really weird ideas that I wanted to apply. So let's just look at a little example program first. So here's a function that's called ksum. It's going to take k and L, and it's going to match on L if it's empty. Then we'll return 0. Otherwise, we'll see a cons of A and D, and we'll have A plus K times ksum kd. All right, so the main idea of Lexburs is that they have this concept called a line. And so the idea is that your program is a sequence of lines, and we have different ways that we can make lines have structure inside of them. So for example, right here we say that there's a line which has a fun, there's a function application of ksum, which is k and L. Notice that comma is not here. Comma is going to be built in to the parser, so it's going to know about comma. And then notice that we have this colon right here, which turns into indent, and then inside of indent is the whole other thing. So this is sort of the first big idea. So how when you're at a shell script, or you can write a line and then you put a slash at the end, and this slash cancels the new line and makes it so that the next line is actually part of the original line. The whole idea of Lexburs is to take that idea and run with it. So the idea is that you're a line right as it ends, whatever the last character is, that's if there's one before a new line, it's gonna change the interpretation about what comes next. And if you have a colon, then it's gonna mandate that you must indent line, and after you mandate that you indent, then the entire sequence of lines that come after that will have to be terminated by a blank line all by itself, and then all of that content will be inside of the indent. And that's why we get this indent with stuff inside of it. Now the next idea is that you can have a slash, and what the slash does is it continues on to the next line with a mandatory indent. So we must have an indent right here, but with these two characters because we ended in a slash. And then we can have a bar, and bar is going to be something similar, where it's going to say, okay, well when you have a bar, that means that we're going to have a sequence of bars that line up at exactly the right character, at exactly the same character as the previous bar. And then there's a line after them. And so this is an empty with a colon, and then that colon, we have a semicolon obviously as the way to blast away the rest of the line as a comment, and so on. Okay, let's look at another example. So here's that timed thunk thing again. Pretty much not a lot new here, except that we have the text form, which I'm very passionate about trying to add text everywhere. And so we just have braces, and then boom, right here's text with a escaping form of an @ Notice that it shows up as #text and #test escape. Okay. Now let's look at one last example of a macro. So the idea of the macro here is that macros are implicitly cased, which is why we use the bar. And then brackets are also going to be special. Brackets are basically going to quote a line. So by quoting this line, right here we say line with line _ e inside of it, this is going to allow us to write macros that consume a line and do something to them. And then finally we have a quote form, which is going to quote something. Okay, so now let's look at some of the details of Lexburs. And I'm going to describe them very differently. I'm not going to describe them with like a grammar. I'm going to describe them with examples and stuff. So the idea is that Lexburs have new categories that are not like other languages. So there are what are called leaders, units, sequences, groups, lines, and text. So let's go through these. So leaders are things that are distinguished by whatever their first character is. So for instance, like an identifier is a leader because it doesn't start with a number or an operator. Numbers are leaders, they start with numbers. There are, characters, like individual characters will start with like #/. And then there are embedded versions of all the other categories. So for instance, if you start with a parenthesis is going to open up a group, and a bracket is going to open up a line. So I don't want to get into all the details here. You can look at the proposal for this, but basically the idea is that leaders are sort of like the atoms in our language. Now the thing that's kind of interesting about leaders is that they have this category called units, which are leaders that are followed by another character. So for instance, when you have a leader followed by a left parenthesis, then this is going to open up a group that is like attached to the previous leader. That's going to be like a function call. And then if you have a dot at the end of a leader, then that is going to open up another unit, which is why we can get a sequence of dots all adjacent to one another. Now, the next concept is called a sequence, which is just a series of groups separated by commas. So this is where commas are built into the language. And then next we've got groups, and groups are a series of units separated by spaces, and they're going to be parsed with infix notation. So notice that this is now mandating that infix notation can only appear in like certain positions. You can only appear when you're inside of a group, and to get a group, you've got to have, the only way to get a group is to be in a sequence. A sequence is a series of groups separated by commas, so commas are going to get you then, and then a left parenthesis is going to open up a group in function position, and also an embedded version of a leader is going to, a left parenthesis there is going to also open up a group. So notice that this language, this syntax is like extremely context sensitive. So a left parenthesis, you don't know what it means by itself. It could be inside of text, in which case it's just a left parenthesis. It could be to the right of a character symbol, which means it's it's like a quotation of that. It could be in a leader position, so it's going to open up a group, or it could be to the right of a leader, which means it's going to open up like a function call group. All right. So then we get lines, and I want to spend most of my time talking about lines. So lines are a series of units that are separated by spaces, and they always end in a follower. So let's look at a bunch of examples of line followers, because they're kind of the most interesting thing. So there's just a new line. So a new line is going to completely separate them. So here are two different lines, foo, bar. So foo is a leader, which is also a unit. Bar is a leader, which is also a unit. Zig and zag are also that. And so this is one line, foo bar, and another line, zigzag. There are slashes, and basically what a slash does is it makes it so that this line continues on to the next line in the file, or in the stream, with a mandatory indentation. And by the way, in Lexburs, indentation is always exactly 2 space characters. So this right here is also 2 lines. These 2 programs are indistinguishable after parsing. You can't tell which one you got. Next we got and so and is like slash, but does not have a mandatory indentation. So this is 2 lines, foo bar baz, and zigzag. So again, you couldn't tell the difference between foo space bar space baz, foo slash bar slash indent, again, baz, and foo and bar and baz. So the idea here is that when you are writing an L-exprs, you're like thinking, okay, well, how am I going to end this line? And any given line, you want to look back to the previous line and say, well, this is how it attaches to it. Okay, next we got colons. And what colons do is colons, the next line is a mandatory indent, and it's inside of it as one unit. And then here's something that's a little bit subtle, which is that the line afterwards is also part of it. So basically, when you have a colon, that means that you are going to parse a block of indented lines, and then once that indentation ends, you now continue the original line. So this is going to be parsed as if x less than y, and then an indent group, which is going to have a list of f and x, and then it's going to have else, and then it's going to have another indent group with g and y, and then because it ends, then now this group is over. Sorry, this line is over. So this is one line of a program that has two embedded lines which are indented. Next we got at. And so what at is going to do is it's going to have an indented text quotation. And it can have any number of lines, and it can escape with at. And like colon, the line that comes afterwards that is unindented is part of the original. And this is sort of like a rule of Lexburs. This language, by the way, is extremely carefully crafted with lots and lots of examples. All right, finally we got bars. And what bars do is they establish a sequence of lines which match up in their indentation and continue on to the next one. So notice that this one has to be in the exact same spot as that line. Text, it's still limited by braces, and you gotta escape. And that right there is Lexburs. Overall, I think that Lexburs are kind of cool. They have, I think, a relatively simple parsing algorithm, relatively simple to keep in your head. They produce what I think are pretty programs, but I would say that their main disadvantage, and same with the disadvantages of C-exprs, is that they don't push the limits of macrology. So what I mean by that is that one of the things that we're going to hear in a little bit about rhombus is that, or rather the sapling and shrubbery notation, is that they really go whole hog into the Honu style of having macros that consume their siblings rather than imposing a strict grouping. And I think that this is a very interesting thing that we've discovered as part of the the Rhombus Racket 2 project. So hopefully this has been interesting, and peace out.
Hey everyone. So, time for questions for me.
I can feed you the questions if you'd like.
Yeah, great. Thanks.
I see there's a question in the doc, which is, so you showed an example with if else. So this is about L-exprs. What if it was when and when? So a when in place of the word if and else. And so how would, does the first when consume the second when in that case?
Yeah. So absolutely it would. And this is kind of one of those things that is a little bit ugly, where you really want if and else to be like one thing, but you also want it to look a particular way, where you want if and else to kind of share the same indentation. So because I started from wanting a program to look a certain way, like definitely like Lexburs are really oriented around, I wrote some example programs and I said, how can I parse that? How can I make whatever that is have an extremely rigid regular structure? And that's what kind of fell out this rule that after you do an indent, the next line counts as part of the first one. And when doesn't look good that way. And so what I would say, and like maybe your next question is like, well, how do I get around it? You get around it with a blank line. So the idea is that, the indentation, what it does is it means that you don't have like closing indicators, right? With C-style programming, you have an opening brace and then a closing brace. And so it's obvious where something starts and ends. And indentation gets rid of that. But the next sort of thing is that syntaxes also have this situation where things like eat their siblings, like if it's kind of a sibling to else, but it grabs it. And so rather than making it so that like if knows that it eats its sibling, you either have to make it so it's part of a larger group, which really gets us back to S-expression world, where you've got to delimit everything beforehand, or you have to come up with some other way of saying that like you always eat your sibling and a way to explicitly end it. And so Lexburs does that with a blank line, basically. So, whenever I wrote larger Lexbur programs, you would get this situation where you kind of like had to add like an extra blank line that you didn't really want to add, or you'd have to look for another way to do the indenting. So as an example, if you're going to have a sequence of whens, maybe you make it so that when actually, I don't know, uses like a bar and you list a whole bunch of different things that, okay, when this situation happens, you do it, when this situation happens. And the semantics of when is, it's not like con, where it will do the first one that matches and ignore the others. This when it really goes down the whole sequence. It's like a guarded block of stuff. So, this is kind of an example of why, Lexburs are not as exciting as the other options. It's kind of a trade-off, right? Because it has the advantage of having a single rule that you always follow, but this rule isn't always nice. In contrast with, what you're going to talk about, Matthew, which is saplings, which are going to approach this exact problem in a different way.
So inspired by things that you had in L-exprs. There's another question being typed. So the question is, if you have ABC and then backslash and the next line indented DEF, that's equivalent to putting it all on one line. Is it a convention whether to write it one way or the other? Is a style guide going to tell you whether to use one or the other? What was the intent?
Yeah. So let me like rewind a little bit, which is just that like in Racket, we do not traditionally mandate that you use particular parentheses shapes in your macros, although it would technically be possible to do so. So for example, taking the cond macro, nothing tells you that the question and answer pairs have to use brackets, but every example that you'll see in the Racket documentation, in fact, uses brackets for that spot. And what you could do inside of like syntax parse, for instance, would be very natural to do this, would be to add a constraint that would look at, I believe it's a syntax dash paren shape, or maybe it's a property. So you can look at that and you can say like, this had better be a bracket. And we don't do that. But part of, in my mind, the goal of dense syntax, where when I say dense syntax, that's kind of the way that I think about C and Haskell and whatnot, where there's a lot more in the syntax, which means that the job of the parser is going to do more, but that stuff is there for you, the reader, to look at. And so if, for instance, we could mandate that you always have to have brackets in this position in the con, then you're sort of like forcing your the programmers to put in stuff for the next programmer. To continue with this a little bit, like in Racket, it would be weird to make a macro that like had its name and then just like made you like write a word halfway through it. You know what I mean? It just said like, oh, you just have to write else there. Like you could do a macro like that, but we don't do that. And if you were to like ask a Racketeer, like, why don't you do that? They would say something like, well, it's not needed. You don't do anything. You don't do anything.
People sometimes do that at first, but they learn not to do that.
Exactly. And this idea that it's not needed is like, you're talking like a compiler. You know what I mean? But the whole point is that humans need that thing. It's useful for them. So I wanted to try to figure out a way to like add lots of these things. And so the idea with C-exprs is that like everyone is going to mandate that it's a particular paren shape because the different paren shapes are going to have a different interpretation in the main language. So bracket is just going to be a different thing. It's not going to be a normal parenthesis. Now, getting back to the original question of Lexburs, like with indent and bar, like those show up in the parse. So when your macro uses those, it's not just invisible. This idea that the notation is invisible, that's really what is underlying all of these alternative S-expression syntaxes, where they basically say, here's a really convenient way to produce something, but it doesn't show up, and therefore a macro can't enforce it. Therefore, the programmer community can't rely on that thing. And with Lexburs, with the slashes and ands, I felt that that was more of a nod to people's different, like styles of how they like writing stuff. And so I wanted those to be invisible. I didn't really write enough programs to decide if that was a good idea. But I think that, like I said, my inspiration is really Shell. And in Shell, the slash is invisible. You can't tell the difference. And so you're sort of adding that because you can't, you're like offended by a really long line. And so I wanted to give a nod for people doing that because I felt like this line-oriented style, it would be very likely to get lines that are really long, and I am offended by long lines. So I wanted to have that be possible to be avoided invisibly.
Right. Someone is asking about the implementation of C-exprs and L-exprs.
Yeah. So for C-exprs, I did not do an implementation of that, mainly because I figured that it would be really obvious to do, except for like nailing down what exactly is the atom notation. That kind of wasn't the hard part in my mind. The hard part was like thinking through writing example programs, and so I didn't do a parser for that. But then there's a parser and an implementation for Lexburs. And it, you can give it programs and it parses them, and it's kind of fine. It just parses though, and it's not like tied to further things. So, preview a little bit. Matthew's going to talk about his prototype. And his prototype is a real parser, but also it attaches to a particular, say, match macro that like knows about its syntax. And so I didn't do that part of it. It was definitely because Lexburs had such a new way of thinking about what a program structure is. There, I felt like it was absolutely necessary to build a parser to make sure that it was really practical to deal with some of the issues that you might see. One of those issues, by the way, which I didn't really talk about in the talk, is that Lexburs need to like really nail down what the operator syntax is and like define which things are operators and how they get merged together. And so it has rules for defining those as fixed in the language. And I'll just sort of briefly say that, which is that rather than like one of the goals that we want is infix notation, right? But having a really complicated infix notation that only deals with like plus, multiply, times, and divide is like really lame. You know what I mean? But so my sort of goal with that was to say, okay, well, I want to make it so that any random middle school kid, the thing that they write means what they think it means. So starting from that goal, what they mean is what they think it means. But I don't want to make it so that we get into the Haskell style line noise where there are like thousands of operators with all sorts of weird things with weird precedences that are hard to internalize. So I basically said, after we go beyond the stuff that everyone already knows about, then you need to put parentheses everywhere. There is no precedence. You can use infix notation, but you got to manually parenthesize it and differentiate, the precedence yourself. And that decision is 100% inspired by my reading of Pirate, which is a language that Shuram worked on for a while.
I spent quite a bit of time with your Lexbur implementation, and we'll talk about how it inspired a response.
Cool.
Yeah, I think we are. I think we ran out of questions.
Good. Okay. Well, it's now your turn, Matthew.
Okay.